Why, hello, my mathematical geniuses. Okay, so today we're going to get into exponential growth and decay. Um, and this lesson's kind of cool because we're going to take what you learned in 30-1. We've already talked about models of exponential growth and decay. We're going to review that, and then we're going to kind of shift it into a calculus concept where we get to do some cooler things with it than what we got to do with 30-1. Okay, but first we want to review what you did do in 30-1. And what you did do in 30-1 was you looked at this equation, y equals a b to the t over p, where each one of these meant something. Y was your final amount, a was your initial amount, b was your rate of increase or decrease, so that if bacteria were doubling, b would be 2. If a population was decreasing by 25%, b would be 0.75. Okay, so that was your rate of increase and decrease. Then t is your total elapsed time, and p is your period time. So it's the time it takes to do something. So what if we were to say a population of bacteria doubles every 5 hours? How many will be present in 7 hours? Then we'd know that b was 2 because it's doubling. I said every 5 hours, so p would be 5, but then my total time would be 7. Okay, so that's just a quick trip down memory lane. Let's try and answer this question then. So a bacteria culture starts with 2,000 bacteria, and after 3 hours, the estimated count is 10,000 bacteria. Presuming a doubling cycle, determine the number of bacteria after t hours. Okay, so what I'm going to do there, I have a starting population, I have an ending population, I'm presuming a doubling period, so I know that b is going to be 2, and I know that my total time is 3. Okay, so when I plug all that in, I get something that looks like this. Okay, now here's what we're going to do. Here's where it gets kind of fun. I want to create an expression for p. Okay, so if I was going to do that, I'd divide both sides by 2,000. And then I'd switch this to log form, right? So I would say log base 2 of 5 is 3 over p. And so then p would be 3 divided by log base 2 of 5. Okay, so what I can do is I can put that right in for my p-value here. Okay, I had to give you a starting population and an ending population, but that was enough information to figure out p. Once I figured out p, I could use that in the equation for other things. Okay. So we started with just let me take my ink off there, sorry. We started with 2 moments in time, the initial moment and the 3-hour mark. Now we have a way of representing p for all moments in time. So we can use this to build an equation where y and t are not known. Okay, so now we have an equation where we start at 2,000. I know what p is, so I stuck p in there, but I don't know t. So now my unknowns are going to be my final population and my t value. Okay, now just because I know where I'm going with this lesson, I want you to think about this for a sec. We said presuming a doubling time. Okay, and when we presumed a doubling time, this became the length of time it took to double. Here's my question for you. There's 24 hours in a day, regardless of whether we divide the hours up if we divide the day up into hours or if we divide the day up into minutes, right? So who's to say that doubling time means anything? Why couldn't I have said my bacteria triple? Or why couldn't I have said my bacteria quadruple? Changing that statement would only change how long it takes to do that. It doesn't actually change how quick they're growing, right? If I say like, I'm just making this up, but if I say I double every 4 hours, is that the same as saying I triple every 6 hours? Do you know what I mean? The growth, the rate of your growth doesn't change whether you look at it through the lens of a doubling time or whether you look at it through the lens of a tripling time or whatever. The doubling time or tripling time is actually arbitrary, because as I change that number, this number will change alongside it to keep whatever the rate is actually the same. Okay, so I just want you to keep that in mind as I keep going here. Okay, so now we're going to take a look at determine the number of bacteria after 2 hours. So that's a time value. So I just plug in 2 for t, and I'm going to solve. So I've got 2,000 times 2 to the log base 2 of 5 over 3 times 2. Type all that in my calculator, you should get around 5,848. Okay, 5,848. Okay, now here's where it gets fun. Rewrite the general equation in base A with base E rather than 2. Okay, so what I want to do is I want to write this exact same equation, except instead of saying I'm going to have a doubling time, I'm going to have a E time. I'm going to have my rate be 2.7818, Euler's number, instead of 2. Okay, well, how would I go about doing that? Let's just think about P for a second. Okay, so we're going to go back to this original equation. We've got 10,000 equals 2,000 times E to the 3 over P. So what I've done is, instead of saying it's 2 in the original equation, instead of calling it a doubling time, I'm saying my rate is E. And then I'm going to rearrange for P, just like I did with the original equation. Okay, so I'm going to divide both sides by 5. I'm going to switch this to log form, but now that it's base E, that's going to be ln, right? So that'll be ln 5 equals 3 over P. And so P equals 3 over ln 5. And so using base E, I can have an equation that says 2,000 times E to the ln 5 over 3 times T. Okay, so again, I just want to reiterate, I know I've kind of given it away already, but when I referred to my rate as 2, this became my period time. When I refer to my rate as E, this becomes my period time. Okay, now what I would like you to do is I would like you to check to see if this actually works. Okay, check it out when t equals 2 with our new equation. How many bacteria do you get? So with your new equation, I want you to plug 2 in for t and throw that into your calculator and see what you get. And you get the exact same answer. Okay, you get that 5,848. It doesn't matter what my rate is, because my p-value will adjust according to the rate I decide. The rate is completely arbitrary. Okay. So why are they the same? Let's just go through this really quickly for a sec so that you understand. Okay, so what I'm going to do is I'm going to take y equals 2 log base 2 of 5 for a second. Okay, so I'm just taking kind of this portion. And we're just going to play with that for a sec. Okay, because they both divided by 3 anyway, right? So I'm going to take I'm going to take y equals 2 log base 2 of 5. I'm going to switch that to exponential form for a second. Okay, so if I was to switch that to exponential form, I'd get log base 2 of y equals, and then the exponent would be by itself. It'd be free, right? Whatever was locked is free. So it would be log base 2 of y equals log base 2 of 5. Now, in 30-1, we talked about a change of base identity. We can change this to base E, okay? And when we do that, what I've done is I've said, okay, this is going to be log base E of y divided by log base E of 2. When we use the change of base identity, we can make any base we want appear. And then on the top of that ratio will be the thing I was originally taking the log of. And on the bottom of that ratio will be the original base. So now I've got log base e of y being ln y. So I can say ln y over ln 2 equals ln 5 over ln 2. And then the fact that they're both divided by ln 2, I could multiply by ln 2 and that would be gone. So essentially I now can convert that to a statement that says ln y equals ln 5. Okay, ln y equals ln 5, which means 5 will equal e to the ln 5. Because now what I've done is I've just switched it back to exponential form. Okay, so switching it back to exponential form, y equals e to the ln 5. Remember though, I started with y in the first place. This said y, this now says y. Y hasn't changed, which means 2 to the log base 2 of 5 is the same as saying e to the ln 5. Okay, e to the ln 5. This is a big deal. This is a big deal because it means it doesn't matter the base we choose. Like it doesn't matter the base of that exponent that we choose. So if that's arbitrary, we might as well make our life easier and choose a base that's really comfortable to work with. Okay, so the rate doesn't actually matter. All we really need to build the equation is the population at 2 different times. Okay, that will give us how it's growing. So can you think of a reason why we would want to use e for the rate of growth in all exponential functions? Well, I can think of 2. If you haven't thought of any, I'll give you some. 2 things. Number 1, we don't want to have to wait around to figure out a doubling time. Okay, right? Using e, we can just get going right on the math. Nobody has to sit there and figure out, okay, when that population doubles and then what exact moment it doubles so that we know what the doubling time is. Okay, all we need is the population at 2 different times. They could be any time we want them to be, right? They could be when the population only increased by like 75%, or just before you say I did something wrong there, I said increased by 75%. So that would be like a rate of 1.75, right? Just in case there's anybody out there yelling at me. Or it could be like that, I went and got a cup of coffee and I missed the doubling time. Well, now it's almost tripled. Well, that's fine. I just need the population at 2 different moments in time, okay? The fact that it doubled or tripled is completely arbitrary, so I'm going to use e instead. The other reason I use e is because it's super easy to take the derivative of. Remember, the derivative of e to the x is e to the x, right? So it makes my math a little bit easier. And so what we're going to do is we're going to change that formula that we chatted about in 30-1, and we're going to turn it into this guy. So y equals y subscript 0, so that's my initial population, times e to the k times t. Okay, e to the k times t. So everything's the same here. Y is your final amount, yo is your initial amount, and then t is going to be your total time elapsed. Okay, k is called the frequency constant. K is related to your period, much like b was in trigonometry. Remember that b wasn't your period, right? But it was related to your period. So if k is greater than 0, it ends up being a growth model, and if k is less than 0, it ends up being a decay model. Okay, and that should make sense, because if k was less than 0, we would have a negative exponent, which would end up being 1 over e instead of e to the something, right? Okay, so let's go back to our bacteria question that we started with. Determine the rate of growth after 4 hours. Now note, that's the instantaneous growth rate at t equals 4. So if I'm looking for a rate of growth, I am looking for the derivative. So I need to take the derivative of 2000 e to the ln over 3 t. Okay, so when I do that, that'll be 2000 e to the ln 5 over 3t times ln 5, right? The derivative of this guy is this guy times the derivative of the inside function. And the derivative of ln 5 over 3t would just be ln 5 over 3. Okay? Sorry, I'm having mouse issues here. Okay. So now I want the instantaneous rate of growth at 4 hours. So just for clarification again, this guy represents the instantaneous rate of growth at any point in time, right? So now I want to plug in 4 to get the instantaneous rate of growth at 4 hours. So in my communication, even though I'm using derivative of y symbol there, I'm going to say the derivative of y at 4, okay? Plug all that into my calculator, and I end up with around 9,174. So after 4 hours, the rate of growth would be 9,174 bacteria per hour. Okay. All right. Now, a bacteria culture has 100 cells after 20 minutes and 600 cells after 1 hour. So new situation, determine an equation to represent this situation. Okay, I've got my moment in time twice, right? I've got my initial is 100, and then after 20 minutes, it's 600. Now, it's 100 after 20 minutes, and it's 600 after an hour. Sorry, I read the question wrong. None of us are perfect. Okay, so those are my 2 moments in time. So I have to figure out what my period is, okay? So what I'm gonna do is I'm gonna call my 100 cells my initial population for a sec, okay? Because the way that equation is set up, I need an initial population and a final population. So I'm gonna call my 100 cells my initial population. Well, if I call my 100 cells my initial population, how much has passed to get to 600 cells? Well, I started at 20 minutes and went to an hour, so that's 40 minutes that have passed. But I want to do that as an hour because I don't want to change my units around. I don't want to talk about minutes in one moment and hours in another moment. So I need to do this in hours the whole way through. So 40 minutes is 2/3 of an hour. Okay, so I'm going to say my initial population is 100, my final population is 600, and that the total time for that to happen was 2/3 of an hour. Okay, and that gives me enough information to figure out what k is. Sorry, I think earlier I said we're going to solve for p. I'm on the new equation now. We're going to solve for k. Same conversation though. Okay, so in order to get to k, we're going to pretend that 100 is our start, and that's exactly what I said there. Okay, so now we need to get to k. I'm going to divide both sides by 100, and then I'm going to switch to log form. So this becomes ln 6 equals 2/3 k, which means k is 3 ln 6 over 2, okay? Or 3 over 2 ln 6, doesn't really matter, but that's what my k value is. So now that I know my k value and I can figure out what my initial population is, okay, so I've got y equals y to the 0 times e to the 3 over 2 ln 6 t. That's where I am so far, okay? All right, so now what I want to do is figure out that initial amount, just like I was saying. Okay, and so what I'm going to do is I know that I could use the 100 cells at 20 minutes, or I could use the 600 cells at an hour. It doesn't really matter. I chose to use the 100 cells. Okay, so what I did was I plugged in 100 here, and for my time, I did 1/3 of an hour, because 20 minutes is 1/3 of an hour. I could have just as easily set this up with 600 cells and 1 here if you wanted to. Okay, I just need one of those moments so that I can solve for my initial population. Okay, so now going to solve for my initial population, I end up with 100 divided by e to the ln 6 over 2. Okay, this was 3 over 2 ln 6 times 1/3. So 3 over 2 times 1/3 is 3 over 6, and 3 over 6 reduces to 1 over 2. That's where that's coming from. Okay, I typed that in my calculator. My initial population was around 41. Okay, so now my equation adjusts. Oh, I didn't write it there, sorry. But now my equation would adjust to y equals 41 e to the 3 over 2 ln 6 times t. That's now what my equation is, and I can use that to figure out other things. Okay, so I want to make sure you've caught the beauty of this, that by using base E, I don't need to sit there and wait for something to happen with my population. As soon as I have 2 moments in time, like this was, I didn't even know my starting population here. This was just arbitrarily 2 population counts that I did, and I was able to create the whole thing just based on those 2 moments in time. All I need is those 2 moments in time, okay? Because the way the bacteria grow is not going to change however label or whatever label we put on it, okay? Okay, so now determine the rate of growth after 6 hours. So now that's just a t value. So I know my equation was y equals 41 e to the 3 over 2 ln 6t. Plug in, I got to take the derivative and I got to plug in 6. So because it asks for the rate of growth, I'm taking the derivative. So the derivative of 41 e to that will be 41 e to that times the derivative of the inside function. The inside function derivative would be 3 over 2 ln 6. And now I just need to plug in 6 for t. So plugging in 6 for t, I get 1.1 times 10 to the 9. Okay, 1.1 times 10 to the 9. Okay? Okay, so an interesting application of this is with investing and borrowing money. So we want to take a look at one more question that involves investment. So $10,000 is invested at an interest rate of 10% per annum. Find the amount of investment at the end of the 4 years if the interest is compounded annually. So the first thing we want to do is figure out k. So I've got y equals 10,000 e to the k at t. Now again, I need those 2 moments in time, right? I have the first one, I start with 10,000. So how much would I have in a year? Well, I'd have 10%. 10% of 10,000 is 1,000. So I know that in 1 year, my investment would be worth $11,000. Okay, so my second moment in time is 1 year is $11,000. So that's what I stuck in for t and for y. That's going to give me enough information to solve for k. Okay, so I'll divide both sides by 10,000. I get 1.1 equals e to the k. Switch that to log form. So that will be ln of 1.1 equals k. Okay, so the equation for this guy would end up being y equals 10,000 e to the t times ln 1.1. Okay, so now I want this to happen for 4 years. So I just plug in 4 for t. And I'm good to go. Plug all that in my calculator and I get 14,641. Okay, 14,641. Okay, now we're going to shift the conversation to compounding quarterly instead of annually. So again, I still need 2 moments in time. With quarterly though, what happens is you get your interest put on every quarter of a year instead of every year. Now, you don't get 10% every quarter, you get a quarter of 10% every quarter. Okay, so that 10% is still annually, but if you're going to compound quarterly, essentially that means your interest rate per quarter would be 10 over 4. Okay, with 2.5%. So you get 2.5% every quarter, so that at the end of the year, you get 10% for that quarter. But because you're putting it on sooner, you're earning interest quicker because you get to your interest gets reinvested sooner, and so your investment can build. Okay, so my moment in time then is at the quarter mark. If t is a quarter, I'll have 2.5% interest gained. Okay, so 2.5% of 10,000 would be 250. So that means in that first quarter, so notice I stuck a quarter in for t, I'd have gained $250, so my investment would be worth $10,250. Okay, so now I'm going to use this equation to solve for k. Divide both sides by 10,000. And then I need to switch this to log form. So I end up with ln of 1.025 equals a quarter k, which means k will be 4 times ln 1.025. So I want you to notice that I now have a coefficient here, and this number has changed. Okay. Okay, so now when I use that formula and I plug in 4 years for t, I end up with 14,845.06. Okay, so a little better than the last one. I'm going to quickly go back to the last one. Remember, you had 14,641. So by compounding quarterly instead, you were able to get another couple $100, okay, out of 4 years. Okay, now here's where we get to a fun conversation. What if it was continuously? Now, first of all, you need to understand that that's actually not possible. That mathematically isn't possible. Usually the best that you'll ever see is compounding daily, which I don't even know if anybody actually does that either. As far as an investment, your credit card, if you owe money on your credit card does compound daily. But compounding continuously is this thought process that we have in math, where let's say we can compound an infinite amount of times, okay? That sort of sounds like a limit to me, but let's have a quick little conversation about what we have discovered so far. If we had 10% annually, the K value ended up being this. Now, what I want you to notice, you didn't see a 1 there, but I stuck a 1 there. What it ends up being is it's the number of compounding periods here times ln of 1 plus whatever your rate was divided by your compounding periods. Now, if I got that as a number, we get 0.095. Okay, if I just throw just that into my calculator. Okay, when it compounded quarterly, this is actually what we ended up having. Now, I didn't show it to you like this, but I'm again trying to get you to see the connection here. I said it was 1.025, but that 1.025 was actually the interest rate divided by the number of compounding periods, and then we added 1 to it, right? And then we ended up with that number of compounding periods as a coefficient in front of ln. Well, that's why I put the 1 here, because essentially it's the same thing. It's just we had a coefficient of 1 and didn't bother. Okay. So in that thought, let's go to compounding daily for a second. If I compounded daily, that would be 365. So it'd be 365 ln 1 plus 0.1 over 365. Now, when I put that in my calculator, I get 0.099. Now, take a look at these numbers. When I compounded annually, it was 0.095. Then I got up to 0.098. Then I got up to 0.099. Essentially, what I want to do for compounding continuously is I want to see the limit as this approaches infinity. Okay, so play around with that for a second. Just keep trying some numbers. Are you gonna, can you see a cap, I guess is what I want you to try and see. Okay, if you have a graphing calculator, you could also graph and try and figure it out that way. Okay, but what I want you to notice, what happens as the number of periods approaches infinity? The K value turns into the interest rate. Okay, the K value caps right at the interest rate. I had a 10% interest rate. My K value here would cap at 0.1. Okay, so if I want to figure out the interest continuously, my K value just becomes the interest rate. So it becomes E to the 0.1 T. Okay, so now if I use 4 years here, 10,000 times E to the 0.1 times 4, I get a continual interest rate investment of 14,918.25. Now, again, this couldn't happen. I couldn't actually compound continually, but it shows us what the absolute cap would be with that interest rate. Okay, it's more a mathematical conversation than a financial conversation. Although they do use this in financial conversations, you will notice. Okay, let me just go back for a second. This was 14,918, and I didn't do the daily one with you. Let me do the daily one with you right quick. If this was daily, I'll just show you the difference. It would be 10,000 times E to that would be 365 ln of 1 plus 0.1 over 365 times 4. So it'd be, the daily interest rate would be 14,917. So the difference between daily interest and forever continual interest over 4 years is like $1. Okay, so this is more a conversation of how far can we take the limit mathematically. Okay, but that's what compounded continuously refers to. Okay, so here's your homework on this stuff. Take your time, make sure you go through it, and make sure you connect with me if you do have any questions. Okay, have a great day, guys. Take care.